So let me continue discussion on MOS VLSI process. In the last lecture, as I remember, I discussed on the topic of hot carrier effects, which are a severe problematic effect in MOS or CMOS VLSI circuits. These hot carrier effects arises because of the short channels, because channel length is going down day by day, and now normal channel length is 0.25 micron available. In nowadays it is 0.18 micron channel is also available. With this small channel devices, I told you for the supply voltage, if it is not going down, if it is a 5-volt supply, then the channel to drain regions are reverse biased, and so a depletion layer will be there, and in that depletion layer with, if the electric field is enormous high, because the voltage is same, and if the gate oxide thickness is 150 to 100 angstrom unit, so that region, and channel length is say 0.25 micron, in that region, and if the channel doping is not adjusted threshold voltage, so there it has been observed that the field at this drain side of the channel region is excessively high, and that field is of the order of 10 to the power 6 volt per centimeter, or say 5 into 10 to the power 15 volt per centimeter. So with that very high field, there is a chance of the carriers, particularly in NMOS, this is more problematic, because in NMOS the carriers are electrons, and in electrons will be accelerated much, and they will have very high energy. That energy may be equivalent to the KT, thermal energy. That's why those are known as hot carriers. So those carriers will collide each other, and again with this high field, there will be a chances of the impact ionization, and because of the impact ionization, more of the carriers will be developed, and those carriers, generated carriers, some of the carriers may have enough energy to punch through the oxide interface, and it will reach at the oxide layer, and there they will be trapped as a charge centers, and sometimes they form some of the defects in the oxide layer, and because of that the threshold voltage will not be adjusted, it will be variable depending on how much these high energy electrons are trapped because of this effect. And at the same time, some of the carriers may reach to the substrate and giving to the substrate current. Okay, although the substrate to drain is reverse biased, so a current you can get in substrate current. So those effects are detrimental for MOS devices, because the reliability of the MOS devices will be poor. In order to solve these problems, some of the solutions have been predicted, and those solutions are the drain engineering of the MOS devices. And a drain engineering means the doping level of the drain is not abrupt, not in a channel to the drain, channel region and drain region, the abrupt doping level should not be there. Instead of that, a moderate doped drain and then highly doped drain is allowed, which is known as the LDD MOS structure, lightly doped drain. So that means drain will be of two parts. One part will be highly doped, and another part will be moderately doped, lightly doped. So because of that, there will be a gradient of the field, and the field will not be excessively high, and hot carrier effects will be less. I'm not telling that it will be completely absent, but it will be less. But although the lattice or LDD structure MOS devices reduces the hot carrier effects, but it has got lot of adverse effects. What are those adverse problems? Number one adverse problem is the process will be complicated. And why process is complicated, I will discuss one complete lightly drained MOS process. And at the same time, the second adverse effect is that, so drain is now two region, one is lightly doped and is highly doped. So drain to channel resistance will increase because of the lightly doped, and because of increase of drain to channel resistance, so the speed of the devices will not be that high. You cannot improve the speed performance of the MOS devices. Okay, and these are the basic two effects. That means density, and the third one is the density of the devices will not be increased, because you have to give lightly doped drain space. So that space is allowed for lightly doped region. So as a result of which MOS size will increase, and density of the MOS devices, which is the basic attraction of the MOS VLSI circuits, so that will be hampered. Okay. In spite of that, we cannot tolerate the reliability of the devices. So because of the hot carrier effects, threshold voltage shift cannot be tolerated. So we have to use some of the technology improvements so that hot carrier effects is reduced. So one such is LDD MOS process, and now I will discuss the LDD MOS process sequence, and I will explain how the field in the drain side of the channel region is reduced. That is main objective. So now here in the diagram you can see here the lightly doped MOS process. In the first process is low cost, because in a standard MOS process or CMOS process we follow the local oxidation of silicon. Here some spelling mistake, it will be LOCOS, the S is redundant here. So after low cost, gate oxide is formed, polysilicon and plasma oxide deposited, and gate pattern. So low cost means this oxide is formed here and here, isn't it? That means this field region. Field region you have grown a thick oxide. After that you just deposit polysilicon, and polysilicon top plasma silicon dioxide is deposited, polysilicon and oxide. And then gate region is patterned. And how the gate region, because this is the gate region, this is the MOS region, active region. So gate region is patterned using lithography technique. Using lithography technique you pattern the gate region. So that means this is the polysilicon, and the top of this is the silicon dioxide, and rest of the region silicon dioxide and polysilicon are removed. Only the below this is the thin oxide, you know, this is the gate oxide, and that thickness is of the order of 1000 to 150 angstrom normally. And very advanced VLSI CMOS processes, this oxide has gone down below 1000 angstrom, below 100 angstrom also. Anyway, so this through this thin oxide, next step you can implant boron. So a moderate dose implant step is added before formation of sidewall spacer. So here you implant, this is a moderate, these two regions are source and drain region, this is a gate region. So now if we implant through this thin oxide, that means in case of NMOS, what will be the dopants? They will be N type. So then you have to dope phosphorus. Okay, you have to dope phosphorus here and here, this region and this region, and that is a moderate dose you can implant here. And then this step, and then we will follow the sidewall spacer step, and which is also followed in earlier steps already. I hope you remember, that is the salicylated contact structure. I used the spacer, sidewall spacer technology, and we use some space at the side wall, this side and this side. Okay, so that has certain advantages which already I have discussed. So now this moderately doped region, drain and source region, this step is called a reach through step, reach through. Now coming to the next slide. So next wave graph, you see here moderately doping N, that means phosphorus has been done. So here is the N minus we have written here. Lightly doped N minus region is put between drain and channel. This is the drain and the channel, this is the source and the channel, this is the channel region. Below oxide, this is the channel region. Okay. So now this N minus is put here in between drain and the channel, and its length and doping level can be easily controlled so as to reduce the peak electric field, and with it hot electron degradation. That is our aim. So then we have to adjust the length of this reach through, the doping level of the reach through, and width of the reach through diffusion or implantation. So length, width and doping level of the LDD region is adjusted so as to reduce the peak electric field, and with it hot electron degradation also. Now after this implantation, then next step is polysilicon deposition. Polysilicon is deposited again. So this is the polysilicon. After completion of the LED formation, then we reach through implantation, then again polysilicon is deposited. Okay. Next, formation of oxide sidewall spacer. So this polysilicon is deposited to form oxide sidewall spacer. So this is the polysilicon. Now we oxidize the polysilicon. So because of that oxidation, silicon dioxide will form in this region, and sidewall region also. Here sidewall region also. The polysilicon will be converted into silicon dioxide if you go for oxidation, thermal oxidation. In the next, you see after thermal oxidation, when the polysilicon is oxidized, then what is to be done? The etching of the oxide. And that etching has to be RIE, reactive ion etching, so that selectively it will etch the oxide which is formed from polysilicon. That oxide is etched here in this region vertically. Here, because the growth of oxide here is a highly selective and vertical, is an anisotropic etching. So the sidewall oxide will not be etched because it is directional etching, RIE. Okay. So sidewall oxide will remain. Similarly, from the top also it will remove. So this is known as the sidewall spacer. Sidewall spacer. After the formation of oxide sidewall spacer, then comes source and drain implant. So this is N plus and N plus source and drain. This is implanted here and here. This is N plus source and this is N plus drain, because the sidewall spacer will prevent implantation below this region. Then this region will remain as N minus, this region will remain an N minus. So only the region left outside the sidewall spacer, there it will be implanted N plus and N plus. Okay, source and drain implant. Now silicide contact formation and metallization. Again you deposit polysilicon on top of this structure. So the polysilicon will be deposited here, 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 here and here, everywhere. Now process follows similar to salicide process. Then after deposition of the polysilicon, then you deposit metal. So metal and polysilicon will react, and then it will form silicide, and the unreacted portion of the metal as well as the polysilicon is etched away through selective etchant, and that selective etchant for titanium silicide or cobalt silicide are available. So silicide will not be etched, but unreacted metal film will be etched. Okay. So now only the contact regions, source and drain contact region and the gate region, the silicide will form, and the rest of the region silicide will be removed. That is self-aligned silicide, which is known as salicide. So this completes the process of LDD MOS transistor. Okay. Now the problem of the LED structure, as I mentioned, is additional parasitic resistance. Where it is coming? Because this N minus region, this N minus region. Earlier, the N plus source and drain, and the channel is inverted, so there is a direct path between source to channel to drain. Now what happens, because of this gradient doping, N plus and N minus, so total drain resistance here will not be the same as earlier step where only N plus is used. So that is one additional parasitic resistance which is coming into the picture, and which will deteriorate the speed performance as well as the density of the devices because of the reach through length which are using for N minus implantation. An optimization process for the reach through doping depth and length must be carried out, in which the transistor performance must be balanced against device reliability. So on one side device reliability, and other side we found the parasitic resistance as well as space consumption for reach through implantation. So we have to do some compromise in between these two effects so that we can have device reliability as well as we can have less parasitic resistances. Okay, so for that several modification has been done on the standard LDD process, and those modifications are relating only adjustment of the doping level, adjustment of the reach through length and height, etc. Okay, but whatever modification has been done, so it will not be the same as without LDD structure. Okay, same as means so far as the parasitic resistance is concerned, so far as density is concerned. So this LDD structure is also used in CMOS process. Okay, now I will discuss on CMOS process. And a CMOS, you know, this is basically two MOS fabricated side by side. One is PMOS, another is NMOS. Then it is known as CMOS. Combination of both PMOS and NMOS gives you CMOS structure. And CMOS structure, the main advantage of using CMOS is in inverter. We have seen in the CMOS inverter has higher speed compared to the NMOS or PMOS. Okay, the CMOS inverter, there we can use the PMOS as a load and NMOS as a driver transistors. So the CMOS structure, I hope, CMOS inverter structure, I hope you remember. But now here we will confine our discussion how the CMOS means at the same silicon side by side both NMOS and PMOS are fabricated, and at the same time we have to look that performance of both the devices should be good, not at the cost of one. So for that purpose, means to achieve both NMOS and PMOS of higher performance, there are several processes, several modification of CMOS process, namely known as POL CMOS, NOL CMOS and twin tap CMOS. Now I will discuss one by one the structures. Why the NOL, POL and twin OL structures have been evolved? Because we know the requirement of the substrate of N and P channel MOSFETs are different. For N channel MOSFET you need P type substrate. For P channel MOSFET you need N type substrate, because channel will be the N. Phosphorus doped or antimony doped, whatever it is. So because of the requirement of the substrate, we have to go either POL or NOL or twin OL process. Now a simple POL CMOS process is described here. This is the N substrate. On the N substrate is this N substrate you can easily fabricate which type of MOS? N substrate will give you PMOS. Easily you can fabricate here PMOS. For fabricating NMOS, you need P-type substrate. So how can you locally get P-type substrate? So that just by diffusion or implantation. So deep high energy or deep diffusion, high energy high dose implantation is done to achieve a well which is doped with P-type dopant, and then a long drive-in process is followed so that you can get 4 to 5 micron deep POL. So in this POL you can easily fabricate, POL means it's P-type substrate, you can fabricate easily the NMOS, and in the N substrate you can fabricate PMOS. So side by side you are getting both the MOSes. Now after getting the POL, your rest of the jobs, that means process steps, are similar to the either salicylated process or NOL CMOS process or the LDD NMOS process. Those processes will follow, means gate oxide formation, polysilicon deposition, then the reach to implantation, then source drain implantation, then silicide contact formation. Before that you need also the oxide sidewall pressure formation. All those things will follow. One in case of P, and at the same time in case of N. In N case of NMOS you need N-type source and drain implantation. In case of PMOS you know P-type source and drain implantation. Those two will be additional. One source drain implantation will be additional because you are making both PMOS and NMOS at the same time. Now the thin oxides are there. So here process steps are briefly written. POL formation on N substrate. This is the POL formation. Thin oxide and polysilicon deposition, just like NMOS, single NMOS process. Thin oxide and polysilicon deposition. Polysilicon is patterned at the source and drain regions of the PMOS and NMOS transistors. Here the polysilicon has been patterned. Below that you see thin oxides are there. This is the gate oxide. This region is the field oxide. This region is the field oxide. Here is the field oxide. Thin oxide is this below this polysilicon. This is the thin. The hatched lines are the polysilicon. This is the polysilicon. This is on the polysilicon, and below that is the thin oxide. Here is the thin oxide on gate regions only. Okay, polysilicon is patterned at the source and drain regions of the PMOS and NMOS transistors. Now, next step is just P diffusion. P diffusion means this is the POL process, that means N substrate. N substrate means you are getting PMOS here. So for PMOS you need P-type source and drain diffusion. So when you are diffusing P-type source and drain, then you are covering this region. Okay, you are covering this region where you are going to make NMOS. Here this is a POL, that means you are going to have NMOS here. So first you open this region, complete from this end to this end, then you diffuse boron so that you can get source and drain for PMOS transistor, PMOS device, and after that same mask you use, go for lithography using negative resist. So that means this is here mask is the same mask you are using. If you use positive resist, then here window is open. Then if you use negative resist, then here it will be closed. The rest of the region windows will be open, isn't it? Just a replica structure you will get if you change the photoresist, because they are complement, their properties are complementary to each other. So now here after this P diffusion has been done, you covered this particular region using the same mask, photomasking. You cover this region and other region you open. Okay, and diffusion this particular and this particular region is done using phosphorus. So then you are getting NMOS source and drain region. And since here and here also open, so here also N diffusion will take place. So that means here the field oxide is a thick oxide, and those N dopants, N-type dopants will not reach below silicon. Similarly, here the polysilicon will be doped, and that is also good because it will dope polysilicon and its resistivity will be less. Okay, and this region is again field region. So there it will also be doped with N dopants, but since thickness of the field oxide is large, so it will not reach below oxide. Okay, through this region and this region only you are getting N plus source and drain. So now here, what are the steps? Defining all areas where P diffusion is to take place. Defining all areas where P diffusion is to take place. That means this step is known as photomasking. Photomasking, you are opening window here and here. Then step is P plus diffusion for source and drain region of the P MOSFET. Then comes another photomasking to define the areas where N-type diffusion to take place. N-type diffusion to take place is here. So go for another photomasking using negative form of the P mask. Just now I told you the same mask you can use in this step also, but using negative. Now comes N plus diffusion. Here N plus diffusion. Then defining the contact areas. We define contact areas. Then follows metallization and passivation to complete the process. Here in this POL CMOS process, just I described briefly to form the OL region, and in between there are a lot of steps, and those steps I didn't mention. This will be there in high performance CMOS POL CMOS process. That means all those LDD, salicide, this will be there. The oxide pressure. This is a simplest structure as I described here. Okay. Now coming to NOL process. NOL process will form, instead of POL, NOL will be formed. That means substrate will be P-type. P-type substrate. So on the P-type substrate easily you can form NMOS. P-type substrate, N source and N drain can be implanted, so you can get NMOS. But for getting PMOS, you have to have an NOL. So that's why that is known as NOL process. And what are the process steps that will be shown in next view graph? Here you can see here in this diagram that typical NOL process. If you remember the figures in the earlier slides, similar figures also you can draw from this process flow, block schematic process flow. Okay. Now formation of NOL regions. First, define NMOS and PMOS active areas. Field and gate oxidation. Field and gate oxidation. Gate oxidation is known as thin ox. That means thin oxide. That is known as thin ox, means thin gate oxide. Field is the low cost region. That is field oxide. That means after defining NMOS and PMOS active areas, then go for the low cost process. After low cost is formed, then from the gate cleaning the oxide or removing the oxide from the active regions, then you grow good quality thin gate oxide. Then deposit polysilicon and then pattern it. After patterning polysilicon, that means you are defining the gate region. Polysilicon gate process. So polysilicon gate you are defining. After that N diffusion plus diffusion for NMOS. Then using the same mask but negative resist. One is positive, another is negative. So you can make the P plus diffusion also. After N plus and P plus diffusion means source and drain of NMOS and both NMOS and PMOS are both formed. Then next step is a contact window opening, contact cuts, and deposit and pattern metals. Metallization process follows. Then overglass with cuts for bonding pads. That is the passivation and bonding pads formation. So these are the process flow for typical NOL process. Okay. Next is the NOL and POL CMOS inverter structures. How the inverters looks like. So this is the NOL. NOL in NOL looks like, what are the process steps we mentioned in earlier view graph. The structure will be similar to this diagram. So this is the NOL, and this is the VDD, and this is the VSS, and these two gates. The inverter, you know, CMOS inverter, both the gates are connected. This will be input. Source and drain of PMOS and NMOS are connected one. This is known as the output. And the NOL means the PMOS, here source is VDD, and this NMOS drain is VSS. Okay. So this is the structure of the CMOS inverter. If you remember the circuit diagram of the inverter, that you can compare with the cross-sectional schematic, and the connection will be like this. This is the input V in, and V out is the output, and this is the VSS and VDD. VDD is the PMOS, this is the PMOS drain, and PMOS source and NMOS drain are connected. Okay. So this is the NOL structure. Similarly, if you want to have the POL inverter structure, it will look like this. Instead of NOL, here is the POL. Okay. This is source and drain. P region, N plus region, this one. So N plus means this is NOL, NMOS. NMOS source is here VSS, and VDD is POL. This source, these are the VDD structure. This is V in and V out. Okay. Now, if you look into twin tub structure, twin tub CMOS structure. Twin tub CMOS means this is the NOL, this is the POL. Two tubs are formed. And before going to twin tub process, we have to check why we need it. We have to see why we need twin tub. The NOL or POL process has got some limitation. What are the limitation? Because one of the transistor will be good because you are making the well, that well implantation you can adjust doping level, but whichever is made on the substrate, that you cannot adjust separately, because substrate, you have to live with the substrate doping. So that means whichever MOS you are making in NOL, or if you make a MOS in POL, so that MOS, either PMOS or NMOS, whatever it is, that will be that property can be improved by adjustment of the well doping and well depth and well region, but other is left with the substrate itself. So that is the problem of this either POL and NOL process. But in case of twin well process, if you fabricate both the MOSFETs, NMOS and PMOS, in oil region, separately you form oils of NMOS and oils for PMOS also, then you can control the doping level of the oil regions, and as a result of which there is a chance of improvement of the performance of both the MOSFETs, NMOS and PMOS. So that's why twin well CMOS is popular than either NOL or POL CMOS process, but at the cost of process complexity. Obviously, one step is more, which is you are making NOL region. Okay. So that means here the first thing will be defining the actual regions. Then you go for the low cost process, field oxidation, then go for thin oxide, then make the NOL and POL regions. Okay. Here the advantage is mentioned. Twin tub process allows two separate wells to be implanted into very lightly doped silicon. very lightly doped silicon, that is this silicon is lightly doped, the N substrate, maybe this is the P silicon. This allows the doping profiles in each OL region to be tailored independently so that neither type of device will suffer from excessive doping effects. Okay. So performance and both the device can be improved by tailoring the doping level of the OL region, so that is either NOL or POL regions. That is the advantage. Here the inverter structure is shown, NOL and POL, N substrate, the epitaxial layer, intrinsic epitaxial layer is grown here. Then you form NOL and POL, then source and drain of the NMOS and source and drain of the PMOS are created, and then interconnection of the lines will give you the inverter structure. Okay. Two gates are connected here, Vin, this is the VDD, this is the VSS, and this is output. Okay. So I think you are clear why the twin OL is required. Now, in the next step, I will address some problem which is known as the CMOS latch-up effect. This is a severe problem in VLSI CMOS technology. How to prevent the latch-up? Before that, let me spend some time on the latch-up phenomenon. What is latch-up? And this is a destructive effect. And hot carrier effects is not destructive. It will deteriorate the reliability of the devices, but it's not destructive. But CMOS latch-up effect is a destructive effect. Cumulative destruction will take place, and it can spoil the devices. Okay. So let me spend some time on this effect. What is this latch-up effect? A major problem in CMOS circuits is the inherent self-destructive phenomena known as latch-up, in which a very low resistance path is established between the VDD and VSS power lines, allowing large currents to flow through the circuit. Because of this latch-up effect, a very low resistance path is established between VDD and VSS power lines, as a result of which a large current will flow and it will damage the metal contacts and the device will be destroyed. This is the effect. Now we will discuss how this very low resistance path is established in CMOS device. As a result of this latch-up effect, large currents flows through the circuit, and this effect stops functioning and even destroy itself from heat damage, and thus latch-up is a destructive effect. Latch-up arises due to the presence of complementary parasitic bipolar transistors contained in the CMOS structure. A complementary parasitic bipolar transistors will be formed in CMOS structure, and these complementary parasitic bipolar transistors are one PNP, which is vertical PNP, another will be NPN, lateral NPN transistors, and these two transistors will be connected in such a fashion that a positive feedback will be developed. And because of the positive feedback, if the bipolar transistors, parasitic bipolar transistors have enough gain, then a large current will flow from the supply to the ground. And this is similar to thyristor effect. PNP and NPN devices will be interconnected, such that one base will be common to the collector of the other device. Okay, that is the thyristor effect. And how it is formed, let us see into this diagram. Here is the CMOS structure. In CMOS, you see, this is the P plus source and drain. That means this is a PMOS, and here it will be NMOS. Okay, this is a N plus and N plus source and drain. This is a gate. These two gates are connected. So this is the input. Here is the output. This is VDD, and this is grounded. Now here you see the VDD is this point, is a VDD. Now this is VDD grounded. Then this P, and this is NOL. NOL is the N region. So this is the P region, P. This is the N, and this is the P. So this is one PNP transistor. Sorry, this is the P, N, and another P is this one. This is the P. So this P is the substrate. So P, N, N is this OL region, P, N, and P. So this is one PNP transistor will be formed here. This is a vertical PNP. P, N is the OL region, and another P is the substrate, P substrate. So this is the PNP. Here is the PNP transistor. Now another transistor will form, which is NPN. So this NPN this is the N, and side is the P, and this is the N. So this is N plus. This is the P substrate is a lightly doped, and this is again N region, NOL region is a highly doped. So N, P, and N. Okay. So this is the NPN transistor. This is the NPN transistor. So one N region is common, which is the PNP base. PNP base is this is the PNP base. This OL is the PNP base, P, N, and P. This is the PNP base. And this N region also acts as NPN, NPN collector. Isn't it? So that means one base, this is a common. This N region is basically the OL region. And in this particular point, a resistance RS is connected to the VDD. This is the OL. This RS is coming here. RS. Sorry, this will be RA. This will be divided. This will be RW. Yeah. This will be the RS will be from VDD. So this will be RS. Some mistake here. This will be R. I have to write this is RS and this is will be RW. This is inverted. Okay. So now here is the resistance. Anyway, one resistance is connected in this particular point and to the VDD. So it's already biased. Similarly, if you look into this structure, the P region is common. What is the P? PNPP, the substrate. This is the substrate is the P silicon substrate, and the P silicon substrate for the PNP transistor, this is the collector, and this is connected to the base of the NPN, and this P will act as a base because N, P, and N is a base. So this is the NPN. So this, that means we found the collector and base are common in both the cases. Either PNP or NPN, collector and base are the common that is connected. And here is one is the emitter, another is the, and at the same time you see this is a ground, and another resistance is also there. The resistance is the source resistance, the P substrate resistance. So this is this will be basically the RS, and this will be the RW. What that has been interchanged. So now with this thing, you are getting a connection of the transistors, which is in the form of some sort of thyristor action. PNP and NPN, base and collectors are connected. So now the total is some sort of, you can say, Darlington pair connection is also like that. So there, if the gain of the transistor, individual transistors are high, then overall gain of the structure will be beta 1 and beta 2. Then one is the transistor perpendicular PNP. So beta perpendicular is the PNP transistor gain, and another is the beta parallel is the NPN transistor, which is lateral transistor. So the overall gain will be beta parallel and beta perpendicular multiplying, that will multiply. So it's a large gain, and because of that, large current will flow through this source to drain. That means from source to drain here, a large current path it is getting. And because of the large current, there is a chance of what? Chance of degradation of the contact, because if the power distribution is not more, so the device will burn, heat will accumulate and it will burn. So it is a destructive effect. So now here just what I discussed is written now. Parasitic BJTs in close proximity, these two parasitic BJTs, one is vertical PNP and another is lateral NPN. These are close proximity, interact electrically to form PNPN device structure. PNPN device structure which behave like thyristors. Normally they do not conduct, but a triggering current may forward by a PN junction. Normally they are dormant, but if there is a triggering current, and this triggering current may come from ionization of the carriers, sudden spike in the voltage spike, sudden current spike. Because of those spikes or say ionations of carriers, if suddenly current shoots, then that will be because of the positive feedback effect. So you will find the drain current will be excessively high. The structure will fire. This is known as a firing, just like thyristor firing. In its fire into its highly conductive mode and remain so even after that triggering ceases, because positive feedback loop will work even if you stop the triggering. So this latch-up effect can be reduced by certain techniques. What are the techniques? Those techniques are the parasitic transistors action has to be specified. What are the remedy? First remedy is to reduce the current gain of the CMOS vertical parasitic bipolar transistors, create a deeper or a retrograde well. That is one remedy. Current gain of the CMOS vertical parasitic bipolar transistors should be reduced, and that can be done by deeper or retrograde well. Second remedy, to reduce the resistances of the parasitic current paths, use a heavily doped substrate with devices fabricated on a lightly doped epi layer. That is the second effect, second remedy. Third is to put current sinks in the parasitic current paths. Implant changes through silicon, implant changes through design rules such as putting P+ guard rings around N- channel devices and increasing separation between NMOS and PMOS. If you increase the separation between NMOS and PMOS, then what will happen? Base width increases. And if base width increases, so PNP transistor, base width of the NPN transistor, if increases, so that transistor will not work properly. At the same time, base doping level, if you increase, then the parasitic transistor function will that will not function properly, isn't it? So by these three remedial step, remedial change, you can minimize latch-up risk. Okay. One is the retrograde well, another is the putting a guard ring. That means by putting a guard ring, what you are doing, you are trapping the carriers which are generated because of the latch-up effect. And other one is the base region doping increased. That can be done by adjustment of the channel oil doping. Now next is the radiation effects in MOSFET. That is another effect. When high energy of the order of 1 MeV particles, and those particles are basically photons, electrons, protons, neutrons, alpha rays, beta rays and X rays, strike MOSFET, damages are created in metal, SiO2 and Si. Metals normally don't show any degradation, but high energy neutrons, protons create damage in silicon. All of the radiations have influence on SiO2 and show ionization damage. These are ionization damage because if they damage silicon as well as oxide, so they will deteriorate the threshold voltage changes. EHPs are generated, electron hole pairs are generated, and holes move towards SiO2 and Si interface or trapped in SiO2, which increases interface states. This will increase the shifting probability of the VT, threshold voltage. Increase of interface states results in a reduction in mobility and shift of VT, which is threshold voltage. To reduce radiation effects, a reoxidized nitride process, RNO, have been developed. Okay. These are the MOS technology requirements, past, present and future. In 1992 and 2007. Okay. So you see here in 1998 the channel length VDD, it is going down in 2004 and 2007.1 micron, etc. With this, let me stop.